probably time to start. Welcome, everybody. Today, our speaker is David Martínez Torres, and the title is Coregular submanifolds and Poisson submersions. David, I give you the floor.
Okay, so thank you very much, Anton, for your kind presentations. And also thanks to the rest of the organizers of Global Poisson for the opportunity to give a talk in the seminar. So I'm going to be presenting joint work with Lilian Brambila and Pedro Frejlich. And it is about aspects of submanifolds and submersions in Poisson geometry. And I've structured the talk in 4 parts. I'm going to start the introduction with a very short reminder of basic aspects of Poisson geometry. And I hope that will be enough to get the main ideas of the talk. Still in the introduction, I'm going to present you by means of examples the problems that I want to think about. So we will have a first example of several submanifolds which have an induced Poisson structure from an ambient Poisson structure. And what we will see is that there is some Poisson theoretic property that reflects very differently in the different induced Poisson structures. And in one of them, actually, in a rather loose way. And there will be an analogous similar example for Poisson submersions. So the general theme of the talk will be how to arrange for some Poisson theoretic properties to behave in a reasonable way for induced Poisson structures and for Poisson submersions. And well, in the second part of the talk, I'll discuss some manifolds. So in the zoo of induced Dirac Poisson structures, I'm going to discuss a hierarchy of natural conditions precisely to control the relation between ambient and induced Poisson structures. And one of them is going to be called coregularity, and it's going to play a fundamental role in the rest of the talk. In the third part, I'm going to introduce it for Poisson submersions. And the upshot of the discussion around coregularity is going to be the following. So in Poisson geometry, we have a class of induced Poisson structures, the Poisson Transversals, that have a very nice functorial behavior under morphisms. Now, coregular submanifolds are much more general and don't have this behavior. But what we're going to see is that the setting of coregular submanifolds and Poisson submersions will allow for some sort of weak analog of the nice functorial behavior that Poisson transversals have. And well, in last part of the talk will be examples. They will come mostly from Poisson-Lie group actions because there, for some natural constructions, we have a very effective way of testing whether this coregularity is present. All right, so we know that the classical way to induce a Poisson structure on a manifold is by means of a Lie bracket on its ring of smooth functions, which is a biderivation. And well, a skew biderivation is a field of bivectors. So one translates the Jacobi identity into a PDE, which we call involutivity condition. And my viewpoint on Poisson structures most of the time is going to be this last one. They are going to be, for me, involutive fields of bivectors. Now, whenever we have a Poisson structure, there's an important piece of geometric information that emerges, and these are its Hamiltonian fields. So we have one for each function, or I'll consider sometimes one parameter families of functions. We get it, as we know, plugging in the function or its differential in the first component of either the bracket or the field of bivectors. Now, the Hamiltonian fields, they also define, we know, a singular foliation, a foliation in the sense of Stefan and Sussman by symplectic leaves. And of that data, the only thing that I want to record is just that we do get a partition of the manifold in symplectic leaves. And I wanted to recall how do we get the leaf, the symplectic leaf, through a point, x. So we start with an arbitrary one-parameter family of functions. Then we get the one-parameter family of Hamiltonian vector fields. We take the integral curve, the Hamiltonian curve, through the point, and we collect the time one point, or the whole curve for that matter. And let me finish the introduction recalling some basic examples of Poisson structures. So we know that symplectic structures are Poisson. So those are the invertible involutive bivector fields. the partition is the partition in connected components of the manifold. We also know that on any manifold, we can put the trivial or zero Poisson structure. So their Hamiltonian fields are stationary, and that means that the partition we get is the partition by points of the manifold. Now, these two families, they produce equidimensional partitions, so are what we call regular Poisson manifolds. Now, to produce non-equidimensional ones, one can easily go to bivector fields on surfaces, which are automatically involutive. And there, each zero is going to produce a zero-dimensional symplectic leaf, and then connected component of the zero set is going to be the rest of the two-dimensional symplectic leaves. So let me finish the introduction also by recalling that there are some natural constructions in manifold theory that go through in the Poisson setting, and I just wanted to record the Cartesian product. All right, so I think that should be enough to walk you through some basic examples. So in this first example, what I want to show you is a Poisson manifold with several submanifolds which have an induced Poisson structure. So my submanifold, the ambient Poisson manifold, or the ambient manifold, is going to be R4 and written as R2 times R2, and I'm going to endow it with a product Poisson structure. So in the first factor, I'm going to put that constant bivector field is up to sign the inverse of the standard symplectic form. And on the second factor, I'll put x3 ddx3 wedge ddx4. Now, to the right, you have the full expression of the Poisson tensor, and on top, you have the only non-trivial brackets among coordinate functions. Also, the partition in symplectic leaves, it's the product partition here in green. So you see that we do have two four-dimensional, two open symplectic leaves, and then we do have a one-parameter family of two-dimensional symplectic leaves, filling the hyperplane x3 equals to 0. All right, now I want to consider a couple of natural embeddings. I'm going to embed each factor through the origin. So let's start on the left with the first factor, and I would like to argue that that constant Poisson bivector field is induced by the ambient. And here we have a very quick argument. So notice that the differential of the inclusion sends this Poisson bivector into the ambient Poisson bivector. And this is because we land on the hyperplane x3 equals to 0. So we have a Poisson morphism, and that is an example of a Poisson submanifold. Notice also that what we're doing is collecting an entire symplectic leaf. And in general, we know that Poisson submanifolds, they are characterized as those submanifolds which are unions of open subsets of ambient symplectic leaves, meaning that in such situation, we can induce a Poisson structure so that the inclusion is a Poisson morphism. So let me record here that this is a Poisson morphism, or that is a Poisson submanifold. All right, so let's go to the second embedding to the right. And again, I would like to claim that that Poisson tensor is induced from the ambient. Now this time, the inclusion is not a Poisson morphism, but one can borrow ideas from symplectic geometry to justify the assertion. So what we do first is we work away from the vertical axis, and then we notice that those have planes. They embed in the symplectic leaves in a symplectic fashion, and that means that when we pull back the symplectic form, we can invert it. And upon inversion, you can check that the formula is given by that bivector. Now, all the points in this vertical axis, they go to the one parameter family. Each of them goes to one of the two-dimensional symplectic leaves. And what's important to record there is that those are transverse intersection points. That means that we have to record not just a point, but also the trivial vector space, with, of course, the trivial bivector, which is exactly the return of the formula. All right, so what we have here is an example of what we call a Poisson Transversal. Note that our submanifold is hitting ambient symplectic leaves transversally and in symplectic submanifolds. Now, that is a characterization of Poisson Transversal. Each time that we have such a submanifold, we can produce, by the same means, a Poisson structure. All right, there's a third embedding that is a little bit hidden below that I'd like to show you. So I'm embedding the strip -1, 1 times the real using coordinates xy and sending xy to x, y, x square, x square, y, right? So notice that these two monomials, they have the effect of creating a line of tangencies of this embedding with the first embedding, or if you wish, with the symplectic, ambient symplectic leaf to the origin. And I would like to argue that this inversible Poisson tensor is also induced from the ambient. And we're going to argue in a similar way as we did before. So we first consider points away from the vertical axis, and then note that they go to symplectic leaves in a symplectic fashion, pull back the symplectic form, invert it. The return is this formula. Now, points in the vertical axis, they go to one symplectic leaf. And at each point, we also have to record the infinitesimal intersection. So that is going to be a plane. And we also have to record the induced skew bilinear form. We do that, we pull it back, we invert it, and we see that it abides by this formula. It's going to give us 1/2 ddx wedge dy. So what we have here are several examples of induced Poisson structures, which reflect in a very different way the ambient partition in symplectic leaves. So what I'll do in the second part of the talk is discuss a hierarchy of condition precisely to be able to control the relation between ambient and induced Poisson structures. And one of those conditions is what we call coregularity. All right, so let me go now to a couple of examples of Poisson submersions. So the first example on the left is the cotangent bundle of R2, and it's with the standard symplectic structure. And we know there that fibers are Lagrangian, meaning that if we put the zero Poisson structure on the base, that becomes a Poisson submersion. Now, the only thing that I like you to record from this example is that it takes the unique symplectic leaf in the total space to the infinitely many symplectic leaves of the base. So it breaks it apart in infinitely many pieces. All right, so let's go now to the second example, the submersion in the right. So there, the total space is C2 minus the origin, the base is CP1, and the projection is the usual quotient under the diagonal C star action. I want to put there Poisson structure, and it's going to be given in this time by the wedge of two vector fields. Now, this first vector field A, notice that what it's doing is from the first C factor is picking the Euler vector field, and from the second C factor is picking the opposite Euler vector field. The second vector field J of A, it's its image by the almost convex structure, and there are various ways to argue that that is a Poisson by vector field. So one uses the action. So we do have an action of C star square in the whole picture, and one notices that both A and J of A, they are fundamental vector fields of the action. Now, it's an abelian group, so it means that they are in involution, and then that is convincing to show that the wedge has the involutive property. So it is a Poisson structure. Now, about the base, we also know that's a basic result that Poisson tensors, which are invariant under principal actions, they are projectable. And that is exactly the structure that I'm putting in CP1, so that we do get another Poisson submersion. And what I like you to do now is, again, take a look at the pattern of symplectic leaves and how they behave with respect to the projection map. Now, it's easier to visualize it to work on the real locus of the picture. So that means in the plane y1 equals y2 equals to 0. And first note that capital A, that vector field is tangent to that plane, and it restricts there to a usual linear vector field such that 0 is a saddle point. So there we have the integral curves. So they are like hyperbolas and half axis. Now, J of A also generates an S1 action. So each of these integral curves gives rise to an annulus, right? There are other symplectic leaves that do not hit this real locus, but trust me when I tell you that all of them are annuli. Actually, they are orbits of the anti-diagonal C star action. So what we have here is an example of a regular Poisson structure. And what I like to do now is try to understand how it projects to the base. So notice again that fibers here are lines through the origin in the picture in the real locus. And in particular, I want to look at the half axis, because remember that that half axis, when rotated, is actually symplectic leaf. So that means that that is a Poisson submanifold, meaning that there the Poisson bivector is tangent. So upon projection, it collapses to the trivial Poisson bivector. So we do get a symplectic leaf in the base point. And well, if we now take any other of the integral curves, they are going to be transverse to the fibers of the projection. That means that any of them projects to an integral curve. And well, the whole picture is equivariant, so we can apply the previous S1 action to see the third symplectic leaf in the base. Now, note that in this picture also becomes clear that this Poisson submersion is mapping symplectic leaves of the total space to symplectic leaves of the base. So we do have a couple of Poisson submersions which behave in very different ways with respect to the partition in symplectic leaves of ambient space, of total space and base. And what I would like to do in the third part of the talk is precisely introduce a condition on Poisson submersions to get the behavior of the second submersion, to be able to make sure that leaves are mapped to leaves. And that condition will be called also coregularity. All right, so let's go to submanifolds. So there's plenty of work in the literature on submanifolds in Poisson geometry. So I recorded there a few names, a few authors of papers that were useful for us, well, motivating when thinking about these kind of questions. But there are certainly more papers related to that stuff, and I apologize in advance if I'm not citing all of them. Now, let me also say that what I'm going to say about submanifolds is pretty much contained in the papers whose authors you see on the list. And perhaps our contribution to the subject has been simply clarifying a picture that it was a little bit blurred at places, and also highlighting the importance of the condition of the coregularity condition that I will mention later on. All right, so for the question of trying to induce structures on submanifolds, the Dirac perspective is very appropriate. So that means that rather than thinking of a Poisson structure as a field of bivectors, we will think of it, we will take its graph inside of the generalized tangent bundle. There we know that we get a subbundle that is Lagrangian with respect to this standard symmetric pairing, and which is involutive with respect to the Dorfman bracket. General Lagrangian involutive subbundles are, we know, Dirac structures on M. All right, so let's take now a submanifold X, and let's look at the problem of seeing whether it has an induced Poisson structure. Well, there is some linear data which is present for us right on the spot. So what we have to do is, for each point of the submanifold X, we have to look at its tangent space and the intersection with the tangent space of the symplectic leaf to that point, together with the induced skew bilinear form. And then there's the very hard part of deciding whether that infinitesimal data comes from a Poisson structure or not. And that's exactly the process that I did in the examples in the introduction. So this is our one way of trying to induce Poisson structures. Now, what is very, very unpleasant about the way the problem looks is that this infinitesimal data is normally supported in a non-equidimensional family of subspaces. And the magic of linear Dirac geometry is transforming that family into an equidimensional one. So it becomes a Lagrangian family in the generalized tangent bundle of our submanifold. And also, we know that the problem of having an induced Dirac structure or induced structure boils down to the smoothness of the Lagrangian family. So when the family is smooth, we say that X has an induced Dirac structure. And these are ideas that go back to the work of Courant. Well, we're interested here in Poisson geometry, so let me say that X is a Poisson Dirac submanifold if the Lagrangian family is smooth, and also it comes from a field of bivectors, meaning that those skew bilinear forms that I mentioned before are non-degenerate, or equivalently, if you look at the symplectic annihilators, the condition becomes the following one. Pi sharp of the conormal bundle intersected with the tangent bundle of the submanifold has to be trivial. All right, so to a Poisson-Dirac submanifold, we can associate two partitions. First, we do have a Poisson structure there, so we can think about the partition of in symplectic leaves of pi of x. But we can also think on a second one, which is the smooth path connected components of the intersections of x with ambient symplectic leaves. And it follows that the second partition is refined in the first one. And what the example in the introduction, what the third embedding teaches us, is that this refinement in general is strict. Now, I would like to argue very briefly why these kind of examples are actually something natural, something to be expected. And that has to do with the difference between regular and singular foliations. We know that regular foliation is controlled entirely by its infinitesimal data. In particular, if we have a map from a connected manifold, which is tangent to the distribution, we know that the image is going to be confined in one of the leaves of the foliation. Now, I would like you to look at the example on the right. So that is a singular foliation on R2. It's spanned by ddx and x ddy. Now, to build the leaves, one has to do very much as we did with Hamiltonians. At a given point, we basically take compositions of flows of these two vector fields. If you do that, you'll see that it has three leaves. It's the vertical axis and then the half spaces. Now, what we can do is the following. We can map the reals into the plane, sending y into y squared y. So the image will be a parabola. And if you compute the velocity vector, you'll see that this curve is tangent to the distribution spanned by those two vector fields, yet it is not confined to one of the leaves of the singular foliation. So that is the explanation. All right, so given that these two partitions in general do not agree, so...
Yeah, excuse me, I have a question.
Sure.
Could you go back once? Why is the vertical axis a leaf rather than each point of the vertical axis?
Why is the vertical axis a leaf rather than a point? Is it that I missed something in this example? Actually, you're absolutely right. So I should have come up with a better example. So, well, I think perhaps I'm not making entirely my point with this poor example, but maybe the example of the embedding in the introduction makes the point more clearly. So yeah, apologies for the example. So what I wanted to and I didn't do it, is to show that I mean, we have this delicate problem with singular foliations, which is that the underlying distribution does not control the leaves. We know that it is the flows. And that's the reason why such examples as the one in introduction are possible. Okay. So not a very complete justification, but anyway. So given that those partitions in general are not equal, we make a definition of the agreement. So we say that X submanifold, Poisson-Dirac submanifold is clean if the partitions agree. And one can present this property in different ways. For instance, in the second line, what we're saying is that Hamiltonian curves of the induced Poisson structure are actually ambient Hamiltonian curves, where the function has to be, the ambient function has to extend the function in the submanifold. And there is another characterization that says that the Poisson-Dirac submanifold has to intersect ambient symplectic leaves cleanly in symplectic submanifolds. Now, these first and third viewpoints, you see them in the work of Krajnik and Fernandez already. Let me also point out that this clean symplectic intersection property is not able by itself to produce induced Poisson structures. So it's easy to give examples in which the corresponding Lagrangian family is non-smooth. All right, so given that we have a condition given in terms of Hamiltonian curves, the next sensible thing is to go to full Hamiltonians. So we say that the Poisson-Dirac submanifold is split if one-parameter Hamiltonians for the induced Poisson structure are restrictions of Hamiltonians of the ambient Poisson structure. Now, again, this property can be presented in several ways. You can use, rather than one-parameter Hamiltonians, single Hamiltonians. And that's the way in which Laurent and Gu, Pichereau, and Maheke presented it. You can also present it by means of a splitting of the Poisson bivector. That's the way Kreinik and Fernandez did it. I'm presenting here a slightly different splitting. There are several alternatives. So we call it orthogonal splitting, and it means that the tangent bundle of the submanifold must have a complement such that the restriction of the Poisson bivector there splits in one component tangent to X and another tangent to E, and both have to be smooth. Now, another word of warning here is that, I mean, again, in this condition of the orthogonal splitting, we're already saying that there is an induced Poisson structure because that tensor is smooth. However, the problem of deciding whether a given splitting is orthogonal is as difficult as the problem of deciding whether the Lagrangian family is or not smooth. So what I want to say is that this class of split Poisson-Dirac submanifolds is still difficult to handle. So just one remark, the two first examples that I gave you in the introduction, Poisson submanifolds and Poisson transversals, are examples of split Poisson-Dirac submanifolds. So in the case of Poisson submanifolds, we can say that those are the split Poisson such that any...
David, sorry, I think there is a question of Dima in the chat. Dima, do you want to voice it out or do you want me to read it?
Sure, I can just say it out loud. Does E need to be involutive? That's
not at all. Not at all. No, it's not a condition. I mean, there is a condition, previous condition by Xu, stronger. Where you place, you say we're working here with Hamiltonians. We are not working with the algebroid. You could go up in that hierarchy. We're not doing that.
Okay, thank you.
But that's a possibility as well. So I was telling you that both Poisson submanifolds and Poisson transversals are examples. In the case of the submanifolds, any splitting is orthogonal. In the case of the transversals, the one that comes from the conormal bundle is the only one which is orthogonal. And given that these classes of induced Poisson structures, they have such a nice geometric characterization, it would be nice to have them together in perhaps another class whose presentation is also efficient. And for us, that's the role of the Coregular class. So we call a submanifold Coregular if pi sharp of the conormal is a vector subbundle which meets the tangent bundle trivially. Now, to the left, you have a diagram with the different classes that I've presented to you. So notice that to go from Poisson-Dirac to clean, you simply use the partition in symplectic leaves. From clean to split, you use the Hamiltonians. And then Coregular is a bundle type condition, a very convenient one. And I like to finish this part giving you some reasons why we think that Coregular submanifolds are worth attention. So firstly, they put together Poisson submanifolds and transversals, but also points, and points are convenient in some conceptual reasons. Secondly, well, the definition of Coregular, I didn't start definition saying let X be a Poisson-Dirac submanifold, any submanifold. So that Coregular condition implies the smoothness of the Lagrangian family. And again, you can show, for instance, that it abides by a well-known test of a smoothness of that family that goes back to the work of Courant. And in fact, you can trace back this Coregular submanifolds, the Coregular class, to his work. It's already there. Third reason is that the hierarchy that goes from Poisson-Dirac to Coregular, it does happen to collapse in some very interesting cases. For instance, when the ambient is a regular Poisson manifold. But we'll see also a couple of instances of this collapse later on in the talk. Fourth reason for us is that, well, they are very relevant, as I hope to show you, to Poisson submersions. And the last reason is that very recent work of Gaudens shows that they are also relevant to normal form theorems. Okay. So let me just now go to Submersions. And again, there you see some names. Those are authors of papers that we find very interesting and very inspiring. And again, they are much more in the literature about submersions in Poisson geometry. Now, what I want to do, or my aim is, well, to arrange for a Poisson submersion to take symplectic leaves to symplectic leaves. And for that, I'm going to start with several examples of Poisson submersions that have that property and see what else they might have in common. So my first example is a flat symplectic bundle. So for me, that means that the Poisson submersion has total space and base symplectic. And well, of course, it sends the unique symplectic leaf in a total space to a symplectic leaf. Now, the second example are vertical Poisson structures. So by definition means that on a submersion, we have a Poisson structure in the total space, which is tangent to the fibers. Then if we put the zero Poisson structure in the base, it becomes a Poisson submersion. Also, symplectic leaves are confined in fibers. So it means that the projection collapses into points, which are symplectic leaves. So that property holds also in that example. And my third example is the one that I gave you in the introduction, that submersion from C2 minus the origin to C2-1. And the other thing that they all have in common, it's very easy to guess, is what happens when you look at the fibers. Now, in the case of flat symplectic bundles, we know that fibers are symplectic submanifolds. And those are the Poisson transversals in the symplectic category. In the case of the vertical Poisson structure, almost by definition, fibers are Poisson submanifolds. And in the last case, well, I already showed you that the two fibers that correspond to the axis, those are Poisson submanifolds. And we also saw that the other fibers, they hit symplectic leaves transversally, and they hit them in points. Points are symplectic submanifolds, so they have the transverse symplectic intersection property, meaning that they are Poisson transversals. So what we see is that in all cases, fibers get induced Poisson structures and of a very nice type. And in some cases, they are mixed, they appear mixed. Well, that's one possible reason to give the following definition. So we say that a Poisson submersion is coregular if its fiber sins as submanifolds of the total space, each of them is coregular. And in this next slide, I'd like to present you the main results. So we start with the Poisson submersion. Now, point A says that it is coregular, meaning fibers are coregular submanifolds if and only if they are Poisson-Dirac. So you see here we have a second instance of the collapse of the hierarchy. So when our submanifolds are fibers of Poisson submersions, Poisson-Dirac to coregular collapses. The third equivalence says that we only need to check the infinitesimal Poisson-Dirac condition. Now, B, let's assume that the submersion is already coregular. Now, if we pick a coregular submanifold in the base, then when we pull it back, it's going to be coregular as well. And the restriction of the submersion still will be a coregular Poisson submersion. And I like to interpret this result in light of the functoriality, nice functoriality property that Poisson transversals have. Now, we do know that Poisson transversals are pulled back by morphisms to Poisson transversals, and the morphism restricts to a morphism. Now, that's no longer true for the coregular class, not even if you assume that your morphism is a submersion. But one can interpret this point P in the following way. So suppose that your Poisson submersion pulls back the simplest of coregular submanifolds, which are points, to coregular. Then it will pull back any coregular to coregular, and then will restrict to a Poisson morphism. So this is for us some sort of weak analog of the nice functorial behavior of Poisson transversals under morphisms. And then in the corollary, well, you see the geometric property we were looking for. So leaves go to leaves. So let me walk you through the diagram a little bit. So in the rightmost column, we have our starting coregular Poisson submersion. Now, what we do is simply collecting a symplectic leaf in the base, and we pull it back. Now, symplectic leaf is a Poisson submanifold, in particular coregular. So we know from the previous result that it pulls back to coregular. But also, it's not any coregular, the symplectic leaf. It has better quality, and that implies that its pullback is actually another Poisson submanifold. So what we have here is a square of Poisson morphisms, and we end up in the middle with another coregular Poisson submersion, but now of better quality because the base is symplectic. So it's what we call coupling Poisson submersion, or equivalently, fibers are Poisson transversals. And in the last step, we simply take a point that lies over the leaf through Y and then extract the symplectic leaf and realize that what we get there is another flat symplectic bundle. So in some sense, I mean, this result tells us that we can have the following picture of coregular Poisson submersion. Now, very much as we say that what the Poisson structure is doing on a manifold is just making sense or putting together reasonable partitions in symplectic leaves, one can say that coregular what does is putting together a partition of a submersion on flat symplectic bundles. And let me show you some other interesting result. So for a Poisson submersion, we happen to have three equivalent conditions. The one on the first line is a nonlinear one. Symplectic leaves go to symplectic leaves. And the ones in the bottom are infinitesimal. So to the left, we have the infinitesimal analog of the nonlinear condition. It's a horizontal infinitesimal condition. The Hamiltonian distribution goes to the Hamiltonian distribution. And to the right, we have the coregular properties. It's infinitesimal vertical in some sense. And I told you that we can go in that direction. That was the previous corollary. So we can go here by differentiation. And we can also go or relate the two infinitesimal conditions. And I think there is something interesting going on here because, I tried, but possibly I failed to show you that distributions are not able in general to control singular foliations. We do have examples of submersions of singular foliations which map the characteristic distribution to the characteristic distribution, but which do not map leaves to leaves. And in this situation, the infinitesimal data seems to control the nonlinear one. And one can trace the difference or the reason to the following aspect. Our submersion is not a nonlinear one, it's a Poisson submersion. And for Poisson submersions, using transversals and normal form theorems, we have rather strong constraint. Those normal form theorems tell us that, or give us some control already in which way the foliation is mapped by the submersion. And that control is enough to be able to relate the infinitesimal, horizontal, and vertical conditions. All right. So let me continue by going back to these examples that I had at the beginning of the section. I want to look into them with a bit more care because they are going to reveal an interesting aspect of these coregular Poisson submersions. So I'm going to start with the flat symplectic bundle. We know that, or I already told you that fibers are symplectic submanifolds. And what we can do is put all these symplectic structures together on fibers on a vertical Poisson structure. We can also take the symplectic annihilators, pi sharp of a vertical subbundle. We know it's an involutive subbundle, gives a regular foliation to which we can pull back the symplectic form in the base, and that produces a horizontal Poisson structure. And we also know that the Poisson structure on the total space splits in a commuting pair of horizontal and vertical Poisson structures. And then we can also put on this setting of symplectic geometry very reasonable completeness condition to go all the way to local triviality of the geometric structure, symplectic or strong local triviality. All right, so let me go now with the vertical Poisson structures. So there, by definition, we already have a vertical structure and we do have a splitting, putting the obvious zero horizontal structure. But when we try to go all the way to strong local triviality, we notice something that happens for a general coregular Poisson submersion, namely that we don't have enough information, we don't have enough structure to relate Poisson fibers which lie over points in different symplectic leaves of the base. So that's what happens. And of course, that raises the very interesting question of coming out with natural ways to link, to relate those fibers, and with natural geometric conditions to get that. Well, so let me also go to the example in the introduction, because in that example in the introduction, we don't even have a vertical Poisson structure. So remember that over this open leaf, we have Poisson transversals. Actually, those Poisson transversals had the induced trivial Poisson structure, and of course, they fit well into a vertical structure over the open leaf. Now, when we try to incorporate the leaf over that point, well, we simply see that that's not possibly a vertical Poisson structure, because otherwise we would have a family of zero-dimensional leaves limiting into a two-dimensional leaf. Well, so let me just pause to remind you that the definition that we gave of a coregular Poisson submersion is placing a condition on individual fibers. We don't say anything about the family, and we don't want to, because we don't want to leave aside these kind of examples. All right. In any case, what I would like to do is argue that among the different conditions that one can think of to relate fibers over points in different symplectic leaves on the base, that they fit into a vertical Poisson structure is a very natural one in our context. It's a very reasonable one. So why is that? Well, let's start with our coregular Poisson submersion. So we already saw that it comes with some piece of vertical data. That's the vertical foliation given by the submersion, and then on each of the leaves, the induced Poisson structure. But we also have some horizontal data. So remember that I told you that if we extract a symplectic leaf of the total space, we're going to see a flat symplectic bundle. So we can pick the corresponding flat leaf, put all those flat leaves together, and they fit into a singular foliation, each leaf having a symplectic structure. And there's some sort of duality between these two pieces of data, because you see, in the vertical case, we start with the best possible singular foliation. That's the one given by a submersion. And on each leaf, we put an arbitrary Poisson structure. For the horizontal data, we start with an arbitrary singular foliation, and on each leaf, we put the best possible Poisson structure, which is a symplectic one. Well, very much as it is reasonable to ask the vertical data to fit into a vertical Poisson structure, it's also reasonable to ask the horizontal one to come from a Poisson structure. And the next result shows, not surprisingly, that both problems are one and the same. Those are points A and B, and also they are equivalent to the splitting of the Poisson structure of the total space into horizontal and vertical components, commuting, what we call an orthogonal pencil. And finally, let me just point out that that's the very explicit Lagrangian family whose smoothness has to be checked for the condition to hold. Okay, so I would like to finish this section by showing you a diagram similar to the one that we had for some manifolds, but this time a little bit more colorful. So the blue part of the diagram is obtained by simply picking the diagram that we had for submanifolds and applying it to the fibers of the Poisson submersion. Because they are fibers of the Poisson submersion, we saw that there is some collapse in the hierarchy. So the first thing that we see is simply coregular. And then vertical uncoupling corresponds to those innermost boxes that we saw for submanifolds, which were Poisson submanifolds and Poisson transversals. Now, the boxes in different colors, they represent conditions that one places to relate fibers lying over different symplectic leaves. So the green one is the orthogonal pencil that I mentioned before. The orange one is this almost coupling condition. That one was introduced by Weissman, and what is saying is the following. So the horizontal data is supported in a family which normally is not equidimensional, and almost coupling means that that family is tangent to an ordinary Ereshman connection for the submersion. Now, this red box in the center is the local triviality of the structure. It's local Poisson trivializations. And then the box which is orange to red is a relaxation in which we allow for gauge transforms. All right, so I think that's enough for submersions, and let me just go to the final part on examples. So what I'm going to place myself is in the following setting. So I'll start with G by G, a Poisson-Lie group, M Poisson manifold, and then the Lie group, the Poisson-Lie group acting in a Poisson fashion. And I'm not going to look at arbitrary submanifolds of M. I'm going to look at orbits of the action. And the result that we have is that such orbits, they are coregular if and only if they are Poisson-Dirac submanifolds. So again, you see another instance of that collapse of the hierarchy on submanifolds, when the submanifolds we look at are orbits of Poisson-Lie group actions. And then the third equivalent says that you only need to check the infinitesimal Poisson-Dirac condition at a point of the orbit. That should be enough. Well, so what we wanted to do is to use this small lemma to detect coregularity in some Poisson submersions which are already present in the literature. So let me start by the abelian case and also reminding a very elementary way to produce Poisson structures. So one starts with a vector space, pi vector on the vector space, and an action of the vector space on a manifold, and right away one gets the corresponding invariant Poisson tensor. In our case, we decorated a little bit the structure, so we required the vector space to be complex, the bivector to be positive in the obvious way, and then the manifold to be complex, and the action to be holomorphic. And in such situation, what you can show right away is that if you take complex subspaces, then their orbits are going to be coregular submanifolds. And we did apply this idea to some known Poisson structures on toric varieties. So let me tell you again that the previous way to produce Poisson tensors out of abelian actions, of course, works the same way when the action is on a submersion. And that was noted in explicit examples, for example, in work of Fernandez, Ortega, and Ratio. And Kane, a few years ago, simply applied that idea to a very specific submersion. It's the quotient construction of projective toric varieties. And he defined some Poisson structures on the submersion and studied its properties. Well, what we simply noticed is that if the Poisson bivector you start with is positive, then the submersion will have the coregularity property. Okay, so for the next setting, I'm going to start, or I'll think of G by G a Poisson-Lie group, but also coming with its infinitesimal data in the form of G equivariant Manin triple. Then I'll pick capital K, a closed connected subgroup, and I'm simply looking at the quotient map together with the Poisson structure on the total space. And now, well, in this situation, what one wants to do is to natural Poisson theoretic questions, try to give an answer in terms of the infinitesimal data, in terms of the data of the G equivalent Manin triple. There are some well-known instances in the literature. For instance, one can ask when pi G is projectable, or one can ask when the subgroup is a Poisson submanifold, when it's a Poisson-Lie subgroup, or one can ask when the Poisson tensor pi G is K invariant, and all those answers, they are contained in the infinitesimal data. They are stronger and stronger conditions. Well, in our case, what we did is, provided that the subgroup K was already a Poisson-Lie group, we asked whether it was possible to encode the coregularity condition of the submersion using the G equivariant Manin triple, and well, the answer was positive. So it doesn't really matter much, the formula. It's important that it exists. And we also could encode when the induced Poisson structures on fibers were trivial. And we did apply this idea again to a well-known example in the literature. So we did start with G compact connected semi-simple Lie group with the Lou-Weinstein Poisson Lie group structure, and we looked at the quotient map into the manifold of full flux. Now, lots of things are known about this Poisson submersion. In particular, the leaves are known. So it is well known that the submersion maps symplectic leaves to symplectic leaves. So in particular, we know about our previous result that it will have the coregularity property. And also work of Lou, with explicit knowledge of the leaves, shows that the T orbits, the fibers of the submersion, they get the zero Poisson structure. Well, what we did is simply check these things with just using the infinitesimal path, just using that information in the Manning triple coming from the infinitesimal coregular condition. And well, let me finish with the last slide about associated bundles. So we start with the principal G bundle and the G invariant Poisson structure in the total space, an action of the group by Poisson diffeomorphisms on a manifold, and we form the associated bundle. And we know full well that this construction passes to Poisson geometry. That's a Poisson submersion. And it's not difficult to check also that the coregular condition and the orthogonal pencil, they both also pass to the associated bundle. What's actually quite interesting about the associated bundle is that sometimes, I mean, it acts as a modifier of sorts. I mean, you can see that sometimes there are conditions that the principal bundle doesn't have, but the associated bundle has it, so it improves the principal one. For instance, you can write down very explicitly when in the associated bundle you will have an orthogonal pencil, and there's no need of having it in the principal one. And yes, let me just finish the talk going back to this still for us unresolved issue of how do we do to relate fibers of the coregular Poisson submersion lying over different symplectic leaves of the base. Now, you could think, for instance, of relating them not at the full level of Poisson geometry, but just at the level of the singular foliations. And for instance, you could demand that in your Poisson submersion, coregular Poisson submersion, the Poisson structure in the total space has locally trivial symplectic foliation, singular foliation. And it turns out that we see that condition appearing in some examples. So that's the content of that proposition. So if we start with a principal G bundle as above, which is coregular, then the foliation of the associated bundle is going to be locally trivial, provided, well, orbits of G of the action of G in X, they have to be inside the symplectic leaves, and then either if the orbits of if the principal orbits in P have the trivial Poisson structure, or if the G orbits in X are isotropic, then you'll see that the foliation is locally trivial, and furthermore, you'll have full control on the leaf space of your foliation. And we did apply that in some cases, for instance, to produce Poisson tensors with finitely many leaves on the non-trivial bundle over S2 with fiber S2, using the examples that I showed you before about toric varieties and about the Lou-Weinstein Poisson structure. Okay, so I think that's all that I had prepared for today. So thank you very much for your attention.
Thank you, David. Thank you. Please, questions or comments?
Yeah, I have a question. Some time ago, there's some papers, I think I might have written one of them. I mean, I know I did, excuse me, about something called co-symplectic submanifolds. And those are what, as Tudor reminded me, correspond to Dirac for second-class constraints. Can you say how these are related to your coregular submanifolds?
So I'm not entirely sure, but maybe if I'm not mistaken, in the Dirac case, you might be requiring that the image, I mean that, So you're also requiring some vector bundle condition, if I am not.
Yeah, I think that what it is, and again, I'm not remembering it too well, but so if you have a submanifold, at each point, you look at the tangent space and project it onto the normal space, then the Poisson tensor projects down, forward, and you get a Poisson tensor on the conormal space. And co-symplectic means that that Poisson tensor is non-degenerate.
Is non-degenerate.
So is coregular something like that, that Poisson tensor has constant rank?
Well, I think it might be. I think it might
David,
be.
Are they? I think these are the same thing as the Poisson transversals.
No, they are not the same as the Poisson transversals. I mean, they are weaker than that. In the Poisson transversals, okay, they are not the same. Sorry. So you are not asking non-degeneracy. So now I'm remembering. So what Alan has as co-symplectic are the Poisson transversals, meaning that the pi sharp, which is going to be complementary to the tangent space. So what we're requiring is that the pi sharp, of course, doesn't hit the tangent bundle, but it doesn't have to be a full complement. It may be a subbundle of a smaller dimension. So let me perhaps, Alan.
But it should be a subbundle.
No, it should be a subbundle. So
yeah, so that's
that's a condition. So a couple of things about that. So that theorem about having flat symplectic bundles also allows you to say in which way. So what is the kind of Poisson structure that fibers in coregular submersions inherit? So those fibers lying exactly over points which are symplectic leaves, over zero-dimensional leaves, those are going to be Poisson submanifolds. That means that pi sharp is the trivial bundle. Fibers lying over open symplectic leaves are going to be your co-symplectic or the Poisson transversals, pi sharp complementary. And then points, fibers lying over points in intermediate leaves, those are going to be bona fide coregular. So subbundle of any rank. And I guess, I mean, there's also a notion of regular Poisson submanifold, I think possibly, or pre-Poisson submanifold from Marco, when what you're asking is that the pi sharp is a subbundle, but it may hit the tangent bundle, meaning that you will get something which is Dirac, if it's smooth, but it won't be Poisson in general.
I mean, in co-symplectic manifolds, one of the very interesting properties is that when you take the co-symplectic manifold and you intersect it with a symplectic leaf, any symplectic leaf of the ambient manifold, that is a symplectic leaf in the induced Poisson structure on the co-symplectic manifold.
Yeah, so let me perhaps go back. Oops, sorry, I was on the screen, not on my. So yeah, so exactly. So in that hierarchy, so in what you're saying, I mean, the next weaker step would be saying, oh, let's remove transversal symplectic intersection by clean symplectic intersection. And that's...
The definition doesn't require it. The definition, the formal definition of co-symplectic is the following. You take the annihilator of the tangent bundle to the, let's call that submanifold S. You take the annihilator, right? So that's some subbundle in T star.
Yeah, the conormal bundle.
Right? And now you take the map,
the pi sharp,
that is coming from the Poisson tensor, and you intersect with the tangent bundle of S, and that's zero.
Yes.
Condition one.
I agree.
The condition two is just transversality, but there is no direct sum. It's just the tangent space plus the tangent space to the leaf is the whole thing. That's it.
Yes.
That's the definition.
No, I agree with that. And what I'm saying is that the idea is in which way you weaken that definition in such a way that you get some properties that co-symplectic manifolds have. And I was trying to argue that if you try to go just thinking as a differential topologist, you have trouble because, I mean, the natural weakening will be saying, okay, I'm gonna require that the intersection with the symplectic leaves is clean and symplectic. And that is not a condition that by itself defines an induced Poisson structure. And the good thing about coregular, which is just the pi sharp that you were telling of the annihilator that is not only that, so it doesn't intersect, of course, 0, but must have constant rank. That condition improves cosymplectic. Or generalizes cosymplectic.
I see what you're doing. You're using the theorem I just quoted as a definition. Okay, I got it. Whereas cosymplectic implies all of this.
It implies all of this. Yeah, cosymplectic
it
implies all of this.
Yeah. I got it.
Okay, more questions or comments? David, with those Poisson-Lie examples, could you say again how how widely? So you mentioned this example with the projection from G to G mod T, but I don't know. For instance, if you if you project from G to smaller homogeneous spaces.
Well, you see, we didn't study that at the infinitesimal level. So let me also try to compare the following things. So in general, one of the things that you try or in those Poisson homogeneous spaces is understanding the Lie space. That enough is very, very difficult. And what we're trying to do here is capture a property of the submersion relative to the Lie space without knowing the Lie space, just by infinitesimal means. So for instance, if you would go to any Poisson submersion, no matter which one, whether it's in the context of Poisson-Lie group, and you know for some reason, because you know the symplectic foliations, that leaves go to leaves, then automatically it has the coregular submersion. So our idea was going infinitesimal the other way around. That's why we knew that the Lurvanchen example was coregular, because we knew leaves. And also that's why we know that some examples in the complex setting, they don't have the coregularity condition. You can actually either apply the test or use explicit knowledge of the symplectic leaves. So in some sense, we're trying to encode that thing. Let me also maybe mention make some final remark that, I mean, what is what we are doing here and in which ways you can generalize it? You could try to generalize. I mean, not just thinking about, for instance, the Dirac sample. I mean, what we're starting, the idea is, well, we start with symplectic flat bundles. So you can think that those are in a category morphism between objects which are atoms, like, or transitive objects. And we're trying to make sense of a morphism that restricts to morphisms to all these atomic objects. And what are the things what we need? Well, we need analogs of Poisson transversals for a structural property. Those are like the best possible comorphisms. And we need that for those comorphisms. We have like, fiber product diagrams. We need normal forms. And then the question is, well, for that property to hold, if you have normal form theorems, that normal form theorem is going to lead you to a study of types of comorphisms, qualities in which the comorphism gets properties. And that's the hierarchy of Poisson transversal, coregular, or some things in between. And eventually, if you succeed to prove that result, what you will be doing is, in some sense, extending up to some extent that functorial property for those Poisson transversals, nice comorphisms, to a larger class of comorphisms. So that's the idea behind, that's one way of looking at things.
Okay, thank you. So more questions or comments?
Yeah, I could just say, I think, David, your example of the curve that was tangent to, that didn't sit inside one leaf, I think you just had a typo in the vector fields. It should have been x d by dx and d by dy.
Okay, so
I think that's...
Thank you very much. But it's good that the example will exist in low dimensions to motivate.
Oh, yeah.
Next time I will fix that. No, there is something quite interesting, or there's something interesting about that, because you see, I mean, singular foliations, they are not controlled by the distributions. And that's what we use to produce these funny submanifolds. On the other hand, in the submersion case, we see that the distribution controls the leaves. Now, why in the symplectic case, in the case of the submanifolds, sorry, that does not create a problem, going from the phenomenon in singular foliations to the one in submanifolds? But the reason is that the reason behind, if you want to think that way, is that for the kind of induced Poisson structures that we're going to place, we are veering away so much from Poisson morphisms that we lose any kind of possible constraint. It's just a constraint of smoothness. So there is no trace of morphism of constraint coming from there. We're very, very far from that. That's why those examples exist.
Okay, thanks a lot. Any other questions or comments? Well, David, thank you again for the wonderful talk.
Thank you very much for the invitation.
Yes, thank you everybody for participating. And next week, we'll have Francis Bishop speaking on global Poisson. So thanks a lot, and see you in a week from now. Bye-bye.
Bye-bye.
Bye-bye, everybody. Stay healthy.
Likewise.
Thank you.